Are we going to talk about the test today?
It's like
No, I won't be here Friday.
We don't have class Friday.
We're gonna have class Friday.
So we're going to talk about the test today.
No.
Yeah. I was like,
What's that? Yes.
What is it?
There's a review. There's review problems on the wall.
he is not.
May I
gentle when
ask
it comes to
now
his tests
what
sometimes.
sections /
He just-
chapters it's in?
It's part of being a take home.
Like when do we start?
The last section will be 4.3.
4.3, and we're working on that now. Right?
Yes.
Hi.
Hi.
Don't worry, we have
The first section is 3.5. So 3.5, 3.6.
3.5 was gamma.
3.5 was gamma and chi-square. 3.6 was normal distribution.
Yeah, I know.
And then 4.1, 4.2, 4.3. And we started 4.3 last time.
Okay, so gamma, chi-squared, normal distribution.
Correct.
And what we just did, the
Yep.
multivariable one.
Yep. And then doing covariance and then conditional distributions is what we're going to finish up hopefully today.
And that's 4.3.
That's 4.3.
That's not too bad.
Covariance and what do we finish with?
Like
Conditional distributions. All right, so before I get started on new stuff, I want to talk about last time and the least squares stuff, only because I'm still irritated about it. Okay. I go through things because I think they're important. I've been doing it for 20 years. Okay. I understand that you may not necessarily think it's important or fun to do, but if I do it, I probably think there's a reason why. For the math people, math ed people in the room, can you tell me pedagogically why I might have done that particular example last time, where we went through and did the derivation of least squares? Can you think of maybe some reasons I might have gone through that particular one?
So we have a better understanding of it.
Okay, better understanding of it, that's a good thing. Could there possibly have been any review things I might have done in there? Well, the least squares line might be on the test, and then maybe the derivation is, but were there some review things? When did you start learning lines, for example? Back in high school? What else popped up? Was that 7th grade? Yeah, maybe? Yeah. What other things were in there? What did we use to start with the maximizing? What did I start? How did we start the problem? We did the derivative. We did stuff back in doing optimization that you did in Calc 1 and Calc 3, right? What else popped up in there when we did the expansion of that particular least squares line? Ooh, we had the definition of the variance popped up in there again, right? The actual definition of the formula that we use every time, right? Megan made the great observation before we even started that the least squares line should go through the average of the x's and the average of the y's of a point. And we verified that was actually on there, right? There was lots of good stuff in there. Plus the extra stuff that you're going to need later if you're doing statistical analyses on things for why is the correlation always between -1 and 1? Why is it when those values are closer to 1 and -1 that we get a closer and closer to a linear relationship? Why, when you square the correlation, it tells you the explanation of the error. Why the variance of x doesn't matter, it's the variance of the y that matters, right? All of those things popped up. There's lots of good information in there, and I understand that not very people are interested in doing derivations like I am. I'm a mathematician, I like those things, right? But pedagogically, there was a crap ton in that derivation that tied a lot of things together. So that's why I did it.
Sorry, Dr. Joe.
That's all right. I don't like feeling questioned about why I do things when they have a good reason why. So I just wanted to talk about it, and I needed to get it off my chest because I've been pissed about it for 2 days. So, okay, so I needed to talk about it and get it out because it needed to come out before, I don't know, something got hit. And I don't like repairing holes in walls. So, all right. So anyway, now that I got that out of my chest. All right. Anyway, I don't care that you didn't like it. That's okay. You're allowed not to like it. That's perfectly fine. Okay? But there's reasons why I did it. Okay? And even if it's that particular derivation is not going to be on the test, which it's not, you don't have to worry about re-deriving it on the test. Okay? I don't expect you to go back through it again for that, because that would be something that would be for a much higher level statistics class. That's important to do on a test. Okay? However, the concepts that are in there, very, very important concepts that tie things together, the things that we've done in the past. Okay, lots of things, right? From 7th grade, seventh grade on, lots of things got, right? You've done linear models and other things. Linear models pop up all over the place later on. Anyway, that was what I wanted to talk about. So, before I forget, Haley's got a review session that she put up here for Monday for the test. Should have review problems on Moodle. Yeah, I sent out an email, yes? Okay, good. I was still a little irritated when I put that together, so didn't know if I should send the email or not. So anyway, you got homework problems. Hopefully they don't take too long. I do need to do one thing that will go with at least one of the problems that's in the chapter 15 problem. So let me do that first before we do some more stuff with the conditional distribution. Yes, Marshall.
So the first 2 lines are from a packet, the second 2,
Yeah, the packet 15 I gave you on a previous one last week, and 16 I gave out last time.
Okay, and then the 4.3s are both in the book.
They're both in the book, yeah.
Okay.
Yep.
Joe, can I ask another question about the test?
Sure.
So, a couple days ago, I asked if there would be an equation sheet on the first page again, and you said yes. Is that all of the equations that we've learned so far, or just like gamma and chi-squared
And normal.
and normal?
Yeah.
So it's just those.
Just those.
The rest
On the
of,
homework.
The rest of them. Yeah, the rest of them. Yeah.
but we don't have to, we're not gonna do, you're not gonna be like.
Not for this test.
Negative binomial.
Not for this
Not
test.
for the final.
Okay.
Perhaps. All right. So we've talked about covariance, and like I said, this particular type of problem is actually I think you're gonna like these problems because they're fairly straightforward. So what it talks about is finding the variance of basically doing what we could refer to as transformations of variables, but all we're really interested in is something that looks like a constant times x plus a constant times y. Okay? So just to go through, we'll have a formula that comes up, and actually the formula is very nice. It should remind you of foiling. Okay? So to see that idea pop up here in a second, I do need to go through the derivation. I'm sorry. Okay. If we use the formula for for variance, I mean, what is that the expected value of? If we just use the formula, not the definition, what formula do we have?
For what?
For the variance of a variable.
AX plus BY squared.
Okay, it'd be the AX plus the BY, quantity squared, and then minus the expected value, and then the whole thing squared, right? Cool. So one of the reasons why you can probably start to guess why the formula is going to look like, remind you of foiling. If it does, we're going to have to do some foiling, right? Okay. Notice on this one, I've got to do the foiling on the inside first, correct? Before I start to break apart expected values. Over here, I'm going to break up the expected values and then foil. Okay? So inside here, we'll have a squared x squared, 2ab xy, b squared y squared. We agree with that one? Can I scroll that way?
Oh.
So down.
Was there a reason that X and Y is capital?
Because we use the capital letters to denote that we're talking about the random variables, and we use the small letters to denote that we're talking about a specific instance of the random variable. Remember, the random variable is technically a function. So we're talking about the expected value. We're talking about if we were to take selections from the distribution over and over and over and over and over and over again, what would the average be? So this is representing all of the possible values for x, versus if we use a small letter, we're talking about a specific instance of x. I mean, practically, you don't, as long as you understand the concept, it doesn't matter if you write a capital or a small, but that's why we do the capital versus the small. And then minus, and then we can break up the, remember what we can do with constants in the expected value? We can pull them out, and then over the sums we can break it apart. So inside here we'll have a times expected value of x and b times expected value of y. And then I still have to square that whole thing, so I'll have to FOIL it out too, right? We okay with the algebra from here to here? Not too bad. Now I want to do the same thing in the first term that I just did in the second term. Break it apart and pull out the constants. Okay. So we'll get, let's start over here. A squared expected value of x squared, 2ab expected value of xy, b squared expected value of y squared. So that was just breaking it up over the sums and pulling the constants out as we go. And then the other one we need to FOIL. So we'll get a squared quantity expected value of x squared minus 2ab expected value of x expected value of y, and then minus, if I can write a minus sign, b squared quantity expected value of y squared. So notice that, hopefully you notice that, the two pieces look similar, right? And even better, I wrote it this way purposefully because they're lined up. Look at the first, what looks like a column. What can I factor out of that first column? A squared. What am I left with? The variance of x. I've got expected value of x squared minus expected value of x quantity squared, right? Look at the last column. What do I have in the last column? B squared variance of y, right? Okay. So, and now in the middle, if I factor out the 2ab, what's in the middle? The covariance, right? So, like I said, this should remind, this is actually the formula now. We have a squared variance of x plus b squared variance of y, and then plus 2ab covariance of xy. So there's our formula, which looks like I said, it reminds you of FOILing, right? Which I hope it reminds you of FOILing with that a squared, 2ab, and b squared. This is kind of cool. So if we do an example here, let's say the variance of x is 7, the variance of y is 3, and the covariance of xy is, I don't know, negative 2. And I ask you to find the variance of 2x minus y. So what's playing the role of A? The 2, and what's playing the role of B? Negative 1. Fantastic. Good. All right, cool. So according to this formula, what should we get? 2 squared times 7. Good. Negative 1 squared times 3. Good. Good. Times the negative 2. Good. Yeah, exactly. That's exactly how you would do these. Yep. And so we get what? 4 times 7 gives me 28. 3 times 1 gives me 3. And then plus an 8. So 39. I did my arithmetic right. Is that okay? There's one in your homework just like this. Literally just like this. Okay? It might give you what the variance of the sum is, and you have to figure out the covariance. So you have to solve or something, but it's just like this. One of the things they might throw in there to try to trick you, which is not very tricky, they might put a plus or a minus, a constant on the end of this. If I add or subtract a constant, does that change the variance? No. So you just ignore it. Because again, remember, that if you think about the distribution, all that plus or minus a constant does is a horizontal shift. The variance is a measure of spread, right? Does a shift change how much it's spread by? No, right? So if there's a plus or minus a constant with no variable, you just ignore it in the variance. Changes expected value, right? A shift will change where the average is, but it won't change the spread. Yeah, Michael.
I don't know if this makes sense. Can this be applied to like another variable, so like X, Y, and Z?
Yeah, absolutely. Yep. You would have to. You have to do a little bit more work with it. It's not too bad. It basically you've got extra products in the middle, and break it up a little bit more. It's probably, if you've got 3 variables as opposed to 2, it's probably easier just to go through and do the multiplications and see what it looks like first. But yeah, it absolutely, you can do this for the several variables. So for example, if you had, let's say we didn't have any of the constants in there, maybe you just had an X, a Y, and a Z. Then when you multiplied that out, you would have, if I square this out, you get X squared, and then you get a couple of XYs, and a couple of XZs, and a Y squared, and a couple of YZs, and a Z squared. Right? If I multiply that out. And notice again, I get these 2's that pop up for the mixed terms. Right? And the same thing's going to happen if you distribute that out. So what you end up with is the variance of X, the variance of Y, the variance of Z, and then a bunch of 2's times each of the covariances. Forgot what letter I was writing. Okay. So yes, exactly. You can do it the same way. And then if there's constants in there, you would get the squares of the constants here, just like we did before, and the products of the appropriate constants on each of them there.
That's just theoretical, right? I'm not doing any of those problems.
It's possible there's one in there that has that with 3. It's not too bad though. But you can do this for more. And it's the same kind of formula. It extends. That's a good question. Thank you.
Say
Yeah.
about the square thing?
If there were an A here, it would become an A squared here. And then there would be an A here and an A here. Because that's what the
thing is just extended.
yeah, it's the same thing. So if there was a B here, there would be a B squared and a B and a B here.
Gotcha.
That's how it goes. It's very analogous. Is okay? So let's switch slides. So I was making sure everybody's got everything down that they want down. Trying to keep everything organized because Haley likes it better. This one actually says untitled page because I wanted to add it in. Sorry.
It's okay. You know, 2 untitled pages are better than all untitled.
I don't even remember why the other one was up here. No, it's because it's got the old stuff on it. That was why. All right. Let's look at this one. This is out of the book. This is 4.3-1. We've talked a little bit about displaying PMFs on graphs and then getting the margins. So this one, we want to extend this to conditional distributions. See you, Sam. I don't even know. I don't even know. I don't want to know. It's okay. All right.
If it makes you feel better, I think he has a program that he's doing the back up.
It's
It might not
okay.
make you
It's
feel
okay.
better,
It's okay. right, so we want to plot, where are we going to plot the points at for this particular PMF? Tell me the points at which we're going to plot some dots. Don't worry about the probabilities, just tell me the points.
1,
Okay. Good, so there's going to be 8 points on here, right? One X value of 1 with all of them, and then X value of 2 with all of them, and I just realized I've got my X and Y's flipped, don't I? For what I just put for text marks. Sorry about that, sorry.
I think we can forgive
labels on them. You could.
I could,
You could have.
and then everybody would have been really confused with me.
Yeah, I would not have liked that.
All right, so I'm going to have dots at 1, 1, 2, 3, and 4. 2, 1, 2, 2, 2. I can't really chew things out about being pedagogical and then flip X and Y on you.
That's a big word. I don't even know what that means.
It just basically means like teaching strategies.
Well,
Yeah, that's what it is.
educator.
All right, so those are the 8 dots that we want on there. So what probabilities are we going to put with each of these dots? Are they all equally likely, or are we going to put 1/8 with all of them? No. Okay. What are we going to put in there?
It'll be
Yeah, the sum of the 2 over 32, right?
Yeah.
We're going to plug in the X and the Y. So when we put in 1, 1, we'll get 1/16.
yeah.
Right? So we'll put a 1/16 next to the 1, 1. Right?
Yeah.
Yep. And then we put in the 1, 2, we'll put in 3 30-seconds. And then 1/8 and 5 30-seconds. If I did my arithmetic right, it's just going up by 1 each time, right?
Yep.
And then over here we should have 3 30-seconds, 1/8, 5 30-seconds, and then what? 3. Let's see, what is it? 6:30. Why is my brain not working? 3/16. Thanks. Brain was just really not want to work. I was trying to get to that point. I could not get to 3/16. It just did not want to do it. All right, so that's how we're graphing the joint PMF, right? Okay.
Yeah.
When we do the marginals now, this would be for X equals 1, we would just add these probabilities together, right? Because that would give me the probability that X is 1. It has to be one of those 4. So you would take the 5, the 4, the 3, and the 2 and add them together. So you get 14 30-seconds or 7/16. And then the other ones would be 6 and 5 is 11, and another 4 is 15, and 18 30-seconds, which should give me 9/16. I was just adding, make sure I did it right, because I should know that those add up to 1, right? Okay. And then we do the same thing for the marginals for the Y's, except we'll add horizontally instead of vertically. So we'll get 5 30-seconds, and then that one should be 7 30-seconds. Oops. And then 9 30-seconds, and 11 30-seconds. So that's part A. That's what part A is asking you to do here.
So could you explain like when we're checking if it's independent or dependent?
Mhm.
And like what numbers would you use like when you do our marginal X times the marginal Y? Like would you use your 7/16 or would you use the independent one?
Well, you're trying to see if they're independent or not.
Yeah, like
So to find a counter example that they're not, you just need to pick a pair where the product of the marginals doesn't give you the joint. So if I take the 7/16 times the 5 30-seconds, I'm not going to get a 1/16. So those would not be independent.
So like the inside's the joint.
Right, the inside is the joint and these are the marginals.
So in order to get
So if they were independent, for every single pair of those, it would be always equal.
This isn't.
No. Because if I take 7/16 times 5 30-seconds, I absolutely don't get 1/16. So, And that's just the one counter example that I would need to say that it's not. Okay. All right, so for the second part now, it's asking us to find this funky thing, right? Okay, so this means the distribution of x given a particular y. Okay, so this g of xy, of x given y, for the discrete case is the probability that capital X equals little x given capital Y equals little y. For the discrete case, that's what that means. So remember how we do conditional probability. Now for the continuous case, we're going to use the same concept that we're going to get to at the end, but it won't mean the same thing, and we'll talk about why it doesn't mean exactly the same thing here. Okay? But if I wanted to do this conditional probability, how do we do conditional probability? Yeah, you do the probability of the intersection and divide by the probability of the given, right? So this is the probability that capital X equals little x and capital Y equals little y over the probability that capital Y equals little y, right? Now, in terms of PMFs, what are each of those pieces equal to? What gives me the probability that x is equal to little x and y is equal to little y? The joint PMF, right? So this will be little f of xy, right? In terms of PMFs, what gives me the probability that y equals y? The marginal, right? Which I think for the y, the book likes to use f2 of y. It's the marginal of y. So this is the formula that we actually want to remember for, this is the formula we want to remember for both continuous and discrete distributions. We think about the derivation of it from discrete distributions. The reason this doesn't work for continuous distributions, the derivation doesn't work, is because what's the probability in continuous distributions of the top and the bottom? In particular, think about the bottom. What would be the probability that the variable equals a specific value for a continuous distribution? It's 0, right? So this doesn't make any sense for continuous, but we use the same formula to find the conditional distribution, the conditional PMF, or the PDF. Okay. So this is the conditional PDF for x given y. So I'll write this down. So this is the conditional PDF for the random variable capital X given little y is the way we write it. And the reason why this is capital X, because again, X is representing on a whole bunch of values that X can take on. The reason why we use a little y is because we're assuming that we've observed a single y. This really is a specific value of y, not a distribution of y's. So that's why this is a capital X, this is a little y. Okay? I know it's weird. It'll get better as we go through this stuff. All right, so what this problem asks us to do is, let me see if I can copy this picture down. Maybe. Yeah, oops. It's the distribution of the x's given a specific value of y. That's why it's a little y. Or it's not going to let me undo that, because of course it doesn't. There we go.
Did you press Control C and just copy it?
Yeah, I should have done that instead. You're right. At this point, I'm already committed to doing that. So
He's committed.
I was committed, yeah, or I need to be committed, one of the two. All right. So for the conditional, what this is asking you to do, instead of having these marginals here, Well, I do need the values. But instead of having the marginals here, let's redraw. Let's actually draw. Let's redraw the picture. All right, so for the first case, we want the x's given particular values for y's, right? Well, the particular values for y's are y could be 1, y could be 2, y could be 3, y could be 4, right? So we're going to take these dots and we're going to split them. Let me change the color. Split them into 4 different groups. Okay? All right. So these groups correspond to specific values of y that we observed. Right? Because it's x given a particular value of y. Right? That's what we're given. X given a particular value of y. So given this particular value of y, what are my probabilities here? Well, how do I find these probabilities here? Well, I take the probability that they both occurred and divide by the probability that y occurred, right? So I would take each of these and divide it by 5/32. Right? That's how we do conditional probability, isn't it? The probability of the intersection divided by the probability of the bottom, the given. Right? So if I take 1/16 and divide by 5/32, we get what? 2/5? And 3/5? So this is for y equals 1. The next one would be 3/7 and 4/7. Right? You see what I'm doing? I'm taking, for the first row, that's the given that y equals 1. So I took each of the individual probabilities and divided by the 5/32. For the second row, I took each of the individual probabilities and divided by the 7/32, or multiplied by the reciprocal. Right? So this is the probability that, just think about this particular one. This is the probability that x equals 1 and y equals 2. Right? That's what this dot represents. So to do the conditional probability, I would take the and divide by the given. And we're given the y value. So I'm taking the 3/32 and dividing by 7/32. And that's where the 3/7 is coming from. So the next one up here would be what? The 4/9, and then the rest would have to be the 5/9, right? They're going to have to add up to 1 in each of these rows, right? Because given a particular value for y, it's still a conditional, or it's still a distribution for x. And then up here we'll get what, 5/11 and 6/11? And by the way, here's another way why you can tell that they're not independent. Going up the columns, notice that the probabilities change for the particular values of x. If they're independent, the given information should not change the probability. Right? That's what independent means, right? It doesn't matter what happened for the one variable, the other variable should have the same probability. Yeah, Marshall.
Should we get the same answers if we divide them by the x's?
No.
For this?
No, because those are different distributions.
Okay.
That's what the next part of the problem asked. It actually says to do it the other way around.
No.
And sees what happens. Okay. So I take this and move it down to the next one. And I'll see it didn't work, Ashlyn. Just stuck it up here instead. Thanks, Ashlyn, for the great advice.
Press square like you're gonna type and then you paste it and then it moves.
Ah, gotcha. I just want to teach you. Oops. All right. So for the other one, if we're doing the y given x, if we're given the x's, then I'm going to split it this way. And Marshall, this is why we shouldn't get the same answer. Because I got more pieces to deal with going this way. Okay.
Makes sense.
Okay. So now I need to take each of these and divide it by the x instead. So when we divide the 1/16 by the 7/16, this one gives me 1/7, right? And then if I take the 3/32 by the 7/16, we get 3/14. And then 2/7, and then 5/14. If I did my arithmetic right. And then you would do a similar thing on the right one. But the idea here is we're coming up with these individual pieces as we go along. Yeah.
So these are the conditional probabilities for like each part of the graph.
Yep, they're the conditional ones. So if we know for a fact that x is 1, these are the probabilities of y being 1, 2, 3, or 4. If we know ahead of time that x is equal to 1.
And the ones are given.
And the 1 is the given. Yep. The given for the x. Yep, that's right. All right. See if we can do this for conditional here. Can we go back? Sorry. I didn't do the other column.
Oh, never mind.
Okay.
You didn't do the other column?
No. Do you want me to do the other column? Do we do the arithmetic?
I feel like everybody would do it. Someone else.
No, I like doing things that completely.
You told me to fill it out, so I did.
No, that's
Because we're going vertically, not horizontally this time. It's going this way. These have to add to 1, and these have to add to 1.
Yes, they would have done
All right. We okay? Okay. Can I go to the next one now?
Thank you.
You're welcome.
yeah, that's judge.
All right. Okay, silent judging. All right. Let's look at this particular problem where it's asking us to find the conditional. We're not going to do a lot of these with discrete. We're going to do most of these with continuous. So that was why I went ahead and flipped over to this one. But the concept is the same. When you find the PDF, the conditional PDF, you're going to take the joint and divide by the marginal. And the extra piece of information we have to worry about are the bounds. Okay? So if I want the conditional of y given x, so it's asking us in this case to find, if I do it with a g again, the conditional of y given x, this is going to be the joint divided by the marginal of x. That's the formula. Okay? We're given the joint, right? Okay? So I need to find the marginal. How do we find the marginal for x?
From 0 to 1.
Oop, careful. I have to integrate. What am I integrating for? What
X to 1.
X to 1, good, because I'm integrating over the y's, right? I got to pay attention to those bounds. I still have to pay attention to the bounds, right? The y goes from x to 1, correct? 2 dy.
How do we know that that's our
Well, I got to integrate over all the y's, and this is my bounds for my y's. My y has to be between x and 1.
Oh, we're finding the marginal.
They're finding the marginal, yeah.
We're using the.
I got you.
Okay. So we get 2 times 1 minus x if we go through that, yes? Because it's just a constant, so I just need to subtract the endpoints. All right, so your distribution then, ooh, hey, that was goofy. Your distribution then is 2 over 2 times 1 minus x. This was, the 2 was the joint. The 2 times 1 minus x was your marginal, so you just go 1 over 1 minus x. Now, we do have to be a little bit careful. Not for this one, because I can see that there's only a 1 over 1 minus x in one of the answers. But we have to be a little bit careful, because when we do the double integrals, when you did the x to 1 for the marginal for x's, you just did 0 to 1 for the y's, right? But this is the conditional of y given the x, right? Well, y can still only go from x to 1. That's why the bound here is from x to 1. Because if I'm given a particular x, the way the problem is set up, my y can't get any lower than x, right? So this is my conditional distribution on that domain, on that support. Okay? So don't think it's from 0 to 1, because given an x, I can't get any lower than what that x value is for the y. Okay? So that's important. Now notice that conditional distributions, unlike what we did for double integrals, we said once we integrate it with respect to a variable, that variable goes away. Right? Notice that this conditional distribution here can have both of the variables in it. Because the y is given in terms of the x, there may still be y's in there too. Because here, when we divided by the x, this was f of xy. There could be y's in the numerator. There will be no y's in the denominator. So it's entirely possible that these conditional distributions can have both x's and y's in them. Even though it looks like we tried to get rid of one of the variables. That's what we did in the very previous stuff, right? We got rid of one of the variables in terms of the other. That's not what happens in the conditional distributions. Anyway.
Just to take this a little further. If you're looking for the mean, then would the bounds be from 0 to 1?
If I were looking for the mean for this, for the conditional distribution?
No, for the marginal.
Oh, for the marginal, you would do from 0 to 1, yeah, if you were doing it that way. Yep. But you can actually find the expected value here of y given x. That's actually a thing. Okay? Okay? So, in this case, the y is my variable. The little x is the value we're given. Right? So I would do the integral of y times the PDF, integrate with respect to y, because I'm trying to sum this up over all the y's, and it would be the bounds for my y, which are still x to 1. Okay? So it's expected value, ignoring the conditional part. This is an expected value of y. So I'm going to integrate y over the possible y's. Okay? So it's the same concept as far as that goes, right? Okay? Looks a little goofy because it still has the x's in it, but your expected value here will involve x because y depends on what x is. Right? Think about what your picture looks like. You could go through this particular idea, but think about what the picture looks like. This is your region. X was less than y was less than 1. Right? So notice that here, you've got a lot more possibilities for your y's than you do here. Right? Given a particular value of x. There's a lot more range here than here. So it certainly makes sense that the expected value, the average of the y's, is going to be different up here than it is down here. Right? So it makes sense that when you do this expected value, it's going to have x's in it. No y's, but it'll have x's in it. Yeah, Michael.
So then you can just find your expected value for whatever the x is.
Mm-hmm. Yep, exactly right. And then if I give you a specific, once you come up with a formula, if I gave you actual number for x, you could just plug it into the formula. Yeah, that's exactly right.
Would you do the integration from x to 1 still first?
Yeah, you still do the integration from x to 1 in that case. Yep. Yep. So this one would be set up the same way. Notice I want the conditional function, the conditional density function, the conditional PDF of y given x. So what do we have to find first? The marginal, right? So first you would find the f1 of x, right? So how would we set that up? Okay. Okay. dy, good.
Sorry. 12xy.
There we go.
Well, I start playing.
Nope. Into x squared. And you do get 24x squared. Look at that. So you do the whole thing?
Okay.
Good. I thought you were telling me what the antiderivative was. Sorry. You're good. My bad. You did it all at once. Thank you. All right. Is that it?
No.
No, what do we need to do?
More stuff.
More stuff.
Plug in 12x over that.
Good. 12x over that. Fantastic. So our g given y given x will be your 12x over 24x squared. Get 1 over 2x. Okay. Now I do see 1 over 2x in 2 spots here, right? Yeah, they have different bounds, correct? So which of those bounds do we want? A or B? B, right? Yeah. Because the y still depends on the x. It's y given the x. So it's y bounds that we're interested in. So the y goes from 0 to 2x again. Does that make sense? It's the y bounds that we're interested in. So it's this piece here. I don't even really care about the less than 1. It's this piece that we care about. Is this okay? Okay. Let's
So
look
the
here.
bounds will always be the same.
Say it again.
The answer.
The bounds should be always be the same as what you did for the marginal, yes. Let's see if I can find one. Here we go. All right, so this one's just slightly different, but to give you the idea of what we want to do, I'm not going to go through the whole problem because I know that I'm out of time and Haley's about ready to hold the stop sign.
I only had it out today for Michael.
All
I said I was repurposing it. And I got to use it twice.
right. So notice in this case that we're given the marginal and given the conditional, right?
Yeah.
Okay, we're given f1 of x, right? And we're given the conditional. If I multiply those two things together, what should I get back?
3ky.
You should get which PDF? The joint, right? It's just rearranging the formula, isn't it? Right?
Can you write it down?
Okay, so we know that the formula is this way, right?
Oh, okay,
Yeah, it's just rearranged, right? So they gave us these two pieces, correct? So we can recover the joint PDF, right? Now it wants us to find the other conditional. It wants us to go the other way.
So we have to find the PDF and then take
So you would find the PDF for the marginal for the y and divide the joint. Right? So I'll do this one next time so that you can see it. That's the idea. So the first thing we do is multiply the two together to figure out the joint. Find the marginal for y and then divide. I thought you were showing me something. You were just trying to take it off.
It's messing me up that they got a K in there. For what reason is the K in there? Like, they're not asking for what K is.
Well, you might need the K to figure out what the constant needs to be. Because that still has to integrate to 1 when you're done. That's why it's there.
It doesn't matter.
All right, we'll do this one next time. No class Friday, remember, because I won't be here.